And today, the schedule is going to be chapter 12, and then a quiz, which will cover chapters 9 and 10. We'll be doing that around 8:50. And then next Tuesday, we'll have a review for our second test. And we'll have another quiz, which will cover chapters 11 and 12. And then test number 2, which will cover chapters 7 through 12, will be a week from today, next Thursday. All right, so that's the schedule for the next week. All right, so any questions about that? All right, and of course, your video should be on for the quiz today. And if for some reason you're having difficulty, make sure you send me a chat message. Let me know why your video is not on. Hopefully, you're all getting your situation straightened out. If you had some difficulties with your cameras, because hopefully you'll have that all straightened out by next Thursday. Okay, because really should not be. I should be able to see all of you when you're taking your quizzes and tests. All right, so please see if you can get this all straightened out by next Thursday. Right, it's a week from today. All right, so let's get started with the PowerPoint for today, chapter 12. All right, let's see if I can find it here. And for some reason, I don't see it, so hold on one second. Okay, all right, let's see if I can see it now. Okay. Now, chapter 10 and a little bit of 11 dealt with the relationship between two measurement variables or quantitative variables. And that's, of course, when we talked about regression and the scatter plot and correlation and all those topics. What if we have a relationship between two categorical variables? How do we analyze those? And that's what chapter 12 is all about. All right. So let's take a look at some of the the students in the statistics class were asked whether they preferred an in-class or take-home final exam, were then categorized as to whether they had received an A on the midterm. All right. So of the 25 students, 10 preferred a take-home exam, whereas of the 50 non-A students, 30 preferred a take-home exam. How would you display this data in a table? Anybody have any idea? How would you do that? I'm going to enter this information in the table.
Maybe a pie chart?
Pie chart, okay. Okay, now it says in a table, the pie chart is a circle. So yeah, you could display this information in a pie chart, but if we were going to look at it in a chart or table, how would you display it? You'd display it like this, where you would have one variable running along the columns and another variable running along the rows, like that. Okay, that's how you would display it. That's what they're really asking for. All right, it says, suppose the news article claimed that drinking coffee doubled your risk of developing a certain disease. Assume the statistic was based on legitimate, well-conducted research. What additional information would you want about the risk before deciding whether to quit drinking coffee? Now, well, this might be a hard question for the answer. Basically, you want it says it's double your risk of developing a certain disease. Well, the question is, what was the risk of not? What baseline are you using the doubling from? All right. In other words, double your risk. Well, what's the original risk? You know, if you're doubling it, that's really the additional information you need to know. Here's a table here. Study classified pregnant women according to whether they smoked. Here along the rows here, we have smoker and non-smoker, and whether they were able to get pregnant during the first cycle in which they tried to do so. So first cycle, did they get pregnant, or did they take more than one cycle, right? What do you think is the question of interest? All right.
Will smoking like affect being able to get pregnant?
Yeah, absolutely. Yeah. And and basically, you want to compare the we can call it relative frequency, we can call it probability. We want to compare the relative frequency of smoking, um, or whether you're smoking or not smoking, to whether it took you longer to get pregnant. Yeah, something like that. So we'll show you how to do that. All right. Opportunity to look at that. There's another concept called relative risk. All right. A recent study estimated that the relative risk of a woman developing lung cancer if she smoked was 27.9. What do you think is meant by relative risk? And some of these terms are going to be new to you. Maybe they're just not clear.
I would think genetics.
Oh, you're thinking the word relative means
Yeah.
family members. No, they don't mean relative in that sense.
Oh, okay. Right.
Yeah, but that's a good thinking there. Now, the relative here is referring to comparing. When we say relative to something else, we're comparing to something else, right? So maybe we want to look at the risk of a woman developing lung cancer if she smoked versus whether she didn't smoke, all right? The risk of developing lung cancer if she smoked compared to if she did not smoke. That's probably what they mean by relative risk. All right, now the table that we were looking at before, this thing here, this type of table, is called a contingency table. It's a way of displaying relationships between categorical variables. Now, what are in each of these cells? Let's take a look at this table here. Forget about what it's about, just look at the table. Well, the cells, there are 4 cells. Now, it looks like there's more than 4 here, but forget about the totals. You forget about the totals for a minute, you see there's 4 numbers here. Each cell represents an intersection between a row and a column. For example, the 29 here represents the intersection of the row, smoker, and the column, first cycle. So we would say out of the 586 people in the study, then the 586 is the total of everyone. That's the total in the right corner here. Out of the 586, 29 of them smoked and got pregnant in the first cycle. Okay. So, and we interpret all these 4 numbers in the same way. For example, the 288 would be the number of non-smokers who took 2 or more cycles to get pregnant out of the 586. There's 288 of those. And then we have our totals, right? The totals. So the total number who got pregnant in the first cycle out of the 586 is 227. There's 359 of them who took 2 or more cycles. Also, there were 100 smokers in the study and 486 non-smokers in the study. Okay, so that's how you read the table. All right, so that's obviously the first thing that you have to know how to do is to be able to read a table and know what these numbers are referring to. They're all counts, right? We're all counting the number of people who meet these criteria here. So a contingency table is just a table where there is a bunch of counts of people who meet certain criteria, all right? And then there's totaling. Now, the table does not have to be displayed with totals. I typically don't have those. And when I test you, I don't have the totals. So you have to use a calculator and actually add up each of the rows and columns, which is obviously not a big deal to do. All right. So each of the cells, each of the numbers in the table are called cells. Each of the row and column combinations are called cells. Now, typically, and this is just typically, the rows are the explanatory variable. The columns are the response variable. In other words, if you think, as a researcher, there is a cause and effect relationship. Then the variable that's the one that's causing is the row one. So in this example we showed a minute ago, let me go back to it. So the rows would be smoking versus non-smoking. So we think that smoking versus non-smoking is affecting whether you get pregnant in the first cycle or you take more than cycles. That makes sense, right? So the rows are typically the explanatory variable, and the response variable are the columns. In this case, first cycle, 2 or more cycles. Okay, but that's typically how it's arranged. All right, here's a study which was looking at the relationship between taking aspirin and having a heart attack. Right. So the explanatory variable is whether you take aspirin or maybe you were given a placebo. Remember what a placebo is, right? It looks like aspirin, tastes like aspirin, but doesn't have the active ingredients of aspirin. And then we're going to see if over time a person ended up getting a heart attack or not. All right. You notice most of the people didn't get heart attacks, right? That's true, right? Most people don't get heart attacks. Only a small percentage of the population get a heart attack. But there's how many people who studied? 22,071 people were studied. 11,037 of them took aspirin, 11,034 took placebo. You might ask, why is there's some difference there? Probably because some people dropped out of the study. All right, most of the people had heart attacks. And then we also have, did not have heart attacks. And then here's the column that deals with the heart attacks. 293 people had heart attacks. 21,778 did not out of the 22,071. All right. And then you can interpret 104 to mean these are the people who took aspirin. Maybe they took aspirin once a day for a couple of years and then ended up with a heart attack. And then over here to 10,933 is people who took aspirin a couple times a day and then did not have a heart attack. All right, conditional percentages and rates. All right, so we're going to talk a little bit about what that means. All right, for example, if we wanted to know the percentage of the aspirin group who had heart attacks, the percentage of the aspirin group. Now, what is the aspirin group? Let's go back here. That's the aspirin row here. How many people took aspirin? 11,037. We wanted to know the percentage of those who had heart attacks. We would divide 104 divided by 11,037. Okay, so that's the percentage of the aspirin that had heart attacks. Don't fall into the mistake of dividing by 22,071 because that's everybody. That includes aspirin and placebo. So the percentage of people who took aspirin, percentage of people who took aspirin who had heart attacks, 104 divided by 11,037. We wanted to know the percentage of people who did not have heart attacks who took the placebo. It would be 10,845 divided by 11,034. Okay, so those are the what I call conditional percentages. They're conditioned on which group we're looking at. All right. All right. Now, if we were going to do conditional percentages, if we want to know the percentage of people who had heart attacks who were in the aspirin group, how would we do that? We would simply divide 104 divided by 11,037 and then multiply by 100 to get to our percentage, right? Hopefully you all know that by now. If you want to take a decimal and turn it into a percentage, we multiply by 100. This is actually 0.94% of the aspirin group had heart attacks. Now, sometimes what people do, because percentages, not everybody understands percentages very well, they give you a rate per thousand, So 0.94 is, as a percent, is really a 0.94 out of 100 people. Doesn't that make sense if it's a percentage? 1% would be 1 out of 100. 0.94% would be 0.94 person out of 100. We want to know the rate per thousand. We just take this number, that's the percentage, and we multiply it by 10. And sometimes people understand this better. Say 9.4 people out of 1,000 who took aspirin ended up with heart attacks. 17.1 people out of 1,000 took a placebo and had a heart attack. All right. Now you notice by comparing these two here, you can see that almost double the number of people who took the placebo had heart attacks, right? So looks like aspirin does work, according to this study. Right? Aspirin reduces the number of heart attacks. That's why people take it. That's why doctors might recommend it if you have a history of heart trouble. All right, here's another table here. All right, where we have the explanatory variable as gender, males versus females. And then what is the response variable? Whether you drank alcohol in the last 2 hours, all right? And so these were young people who were asked this question, and there were 619 people in the study. Again, the grand total is right here. And these are the number of people who answered in a certain way. So out of the males, 77 of the 481 males said yes. That's, by the way, 16%, right? Divide 77 by 481, multiply by 100, it's 16%. How many females drank alcohol in the last 2 hours? 16 out of 138. Multiply that ratio by 100, you get 11.6%. You could even ask the question, what percentage, overall percentage of males and females drank alcohol in the last 2 hours? It would be 93 divided by 619. Multiply that by 100, it's 15%. Okay. Any questions about how to calculate these percentages? All right. Okay. Going back to this problem here. Okay. We want to know the percentage in the first percentage of this people who got pregnant in the first cycle for the smoker group. It's 29 divided by 100, right? 29%. The non-smoker group, it's 198 divided by 486, 41%. You see it looks like a significant difference here between these two, right? It looks like being a smoker reduced the percentage of people who got pregnant in the first cycle. Fewer people got pregnant in the first cycle if they were smokers versus non-smokers. Okay. Everybody's clear on that? Now, this type of study doesn't prove that smoking caused the delay in getting pregnant if this was an observational study, which it was, by the way. Retrospective means they were looking at past numbers, past data. So if it's observational, cause and effect, we can't conclude that because there could be confounding variables, right, that are influencing both the explanatory variable and the response variable. So we can't make any conclusions about cause and effect, although we could see, it does sort of make sense. It could be, right? The smoking could affect that, but we can't prove it. It has to be an experiment, right, where we can control for confounding variables. All right, so let's look at now some of the calculations, which can get a little complicated. I told you last time on Tuesday that this is a chapter where you may have to read and reread and look at the example problem that I'm giving you until it makes some sense to you. All right, so this is not something you can just put aside and then study in half an hour before the test. It's not going to work for you doing that. For most people, well. Suppose we had population containing 1,000 people, of which 400 carry the gene for a disease. We'll assume there's one gene for a disease. So how can we express the number of people that have the gene? Well, we could express it as percentage. 400 divided by 1,000 times 100 is 40%, right? Makes sense. We can express it as a proportion where we don't multiply by 100. It's 400 divided by 1,000 is 0.4. That's called a proportion. All right, so if I ask for a proportion, you express it as a decimal. If I ask for a percent, you express it as a percent. Yeah. Probability is expressed the same way as a proportion. So probability that if you select somebody at random that they have this gene is 0.4. We can also express it as a risk of carrying the gene. All right. So sometimes if the word risk makes sense in what we're talking about, we could also call this proportion or probability risk. So if you see the word risk, it means proportion or probability. It's also 0.4. All right. So those words, these three words, proportion, probability, risk, give you the same information, ask for the same information at 0.4. Now, here's this thing called odds. You might, if you're familiar with sporting events where there's betting, sometimes they talk about the odds of somebody winning the Super Bowl, the odds of winning the World Series, or whatever people are betting on. Odds are different than probability. All right. Sometimes people use the word odds when they really mean probability, but what do odds mean? Odds means if you're saying the odds of carrying the gene are 4 to 6, what does that mean? Well, we know there's a 40% chance that you carry the gene, which means there's a 60% chance that you don't. Everybody clear on that? So 4 to 6 means is that the 4 represents the 40% who carry the gene, and the 6 represents the 60% that don't. So odds compares the people who have the gene versus people who don't. So when we say 4 to 6, we could also say 2 to 3, or 2/3 to 1 if we divide both of these numbers by 3. But that's what it means. Odds of carrying the gene 4 to 6. It's the 40% group relative to the 60% group. There's that word relative again. All right. And that's what we mean by odds. All right. There's also something called a baseline risk. If we have like a placebo group in a study, we want to know the risk for that group. We may want to compare the risk of the treatment of getting a disease versus the risk of using the placebo. And so when the comparison group, the placebo group, is called a baseline risk, or the risk that's for that particular placebo. Relative risk means that we are dividing the risk of one category to the risk of another. All right. For example, if there are 2 categories of the explanatory variable, all right, we may want to find the ratio of those 2 risks or probabilities by dividing them, and that's called the relative risk. A relative risk of 3 means, for example, the risk of developing the disease for one group is 3 times more than it is for another group. All right. A relative risk of 1 means that the risk is the same for both groups. All right. So, for example, let's look at this chart here, where it says first child at age 25 or older. So this is a woman who's giving birth to their first child, and suppose they gave birth to their first child at age 25 or older. So this was a question on the questionnaire. They either answered yes or no, assuming, of course, they have children. And then they were asked about whether they later on developed breast cancer. Whether they did or didn't. Right? So if we wanted to know, for example, the risk for women who have the first child at age 25 or older, that would be the yes group here, of developing breast cancer, would be 31 divided by 1628. That's the same thing as the percentage, right? The percentage of women who gave birth to their first child at age 25 or older who developed breast cancer would be 31 divided by 1628 divided by 100, multiplied by 100. In this case, we're not going to multiply by 100 because we're looking at the decimal, the proportion, same thing as the risk. We get 0.0190. And then we have the risk for women who have the first child before 25. That would be the no group here, right? They answered no. That means they had the child earlier than age 25. And the risk is 65 divided by 4540, which is 0.0143. So we want to know the relative risk of these 2 groups. We would divide these two numbers. When we do with our calculator, we end up with 1.33, which means that the risk of developing breast cancer is 1.33 times greater for women who are older than for women who are younger. That's really what it's saying. Let me say it again. For women who were older when they had their first child than for women who were old, who had their first child when they were younger. All right, so it's let's just call it a relative risk. We just simply take the two risks and divide them. Okay. All right, let's continue. What we're doing at the time, looks like we're good. Now this just gets a little complicated. All right, so if you're given a relative risk, sometimes people want to know what percentage more did you what percentage more is that risk? In other words, if you say it's 1.33 times greater for women who had their first child at age 25 or older than women who didn't have their first child at age 25 or older. Another way, some people don't like expressing it this way. They want to say, what percentage more? And that's called increased risk. So how do you do that? You get your relative risk and you just subtract 1 from it and multiply that by 100. In other words, when I say it's 1.33 times greater, it's another way of saying it is there's a 33% greater chance of developing breast cancer for women who have not had a child before the age of 25. A 33% greater chance. You just take your relative risk, subtract 1, multiply it by 100, then you'll have a percentage, and that's called the increase in risk. That's another way of expressing the same thing. All right, so this calculation could, again, you're going to have to probably read this over and over again, unless, of course, you are familiar with these terms. Maybe you've seen it before. An odds ratio. That sounds pretty odd, right? An odds ratio. So what if we wanted to know the odds, first of all, for women having the first child at age 25 or older? What are the odds of it? Go back to that chart. Well, we know that 31 out of the 1628 developed breast cancer. We know 1597 of the 1628 did not develop breast cancer, right? So for the mothers who had their first child at age 25 or older. We want to know the odds of developing breast cancer for this group of women. For the first row, the odds would be 31 to 1597. It would be the people who had breast cancer, the number of people who had breast cancer to the number of people who didn't. That would be the odds. 31 to 1597. For the women who were younger when they had their first child, the no group here, it would be the odds of developing breast cancer would be 65 to 4475. All right. So that's the way you would express the odds for both of those groups. We wanted to have an odds ratio. All right. We would take these odds. We would actually divide these. Take these odds and divide them, each one of these odds, and then divide the odds. All right. Now they show you alternative formulas, but that's literally what you're doing. You're taking your odds, the 31 to 1597 for the first group of women, just divide those two numbers, and then do the same for the women who were younger than 25. And the odds ratio would be the ratio of these two odds. So you would take this number, 0.0194, and divide by 0.0145, and you would get 1.34. So you would say something like the odds of a woman developing breast cancer, if they were older, is 1.34 times greater than the odds for the younger women who had the child when they were younger. All right. That's the odds ratio. So this is getting a little hairy with the math, right? But again, if you're familiar with examples of how to do this and you do them several times, right? Do what's in the book and also do the example I'll be giving you in a couple minutes, then this shouldn't be an issue, all right? Well, sometimes these odds ratios are adjusted to account for confounding variables. Don't worry about that so much. It just explains why we might do that, but I'm not going to test you on that. All right, and these are some common reasons why these statistics, when they're quoted, could be misleading. For example, many times they will leave out the baseline risk, so that you don't know what you're comparing. If we're saying the odds are double, well, double from what? That we need the baseline, right? The baseline risk. Okay. Time period's not of the risk is not identified, so we don't know over what time period we're talking about. And the reported risk is not necessarily your risk. Now, this is actually important here. When we get statistics, all right, it's the overall population we're talking about, the risk. So when you hear about the risk of getting breast cancer, or the risk of getting COVID even, all of that, it's not necessarily your specific risk. Why? Because your situation will be different than other people's situation. So the risk that's reported in the media about anything is an overall average. You might say an overall average for the whole population, but not necessarily the risk for you. All right, so that's really what they're referring to. And then they give examples of each of these situations that you can read through. All right, just examples. Yeah, Simpson's Paradox we will skip. All right, you can read it if you like, but I'm not going to test you on Simpson's Paradox. All right, so forget about that part of it. Formulas, unless you're a formula person, I'm definitely not looking at this. All right, so again, Simpson's Paradox section here, skip that. And then don't worry so much about the idea of adjusting the odds ratio. Don't worry about that either. All right. Now, let me give you an example of the math behind this. So this example will help you, hopefully. And I believe this is an example that is in your book. Let me see if I can have it actually, the number here, but it is in, I believe, in your book. Let me look at the back of the chapter, see if I see it. Let's see. Do I see it here? And I might have gotten this from another book, not in this book. Oh, here it is. So in your textbook on page 271 is this particular chart. All right. So this is called table 12.12. And the problem that's referring to that is problem number 25. All right. So that's what they're referring to here. All right, so this is a contingency table. The explanatory variable are ethnic groups, in this case, African Americans versus whites. And then let's say there was a company that was laying off people, and we want to compare African Americans who got laid off and who did or did not get laid off versus Caucasian or white people who did or did not get laid off with this company. So we had people being asked, what is your ethnic group, and also whether you got laid off. So for example, 130 of the African-American people in the company, that's 1,512 of those, said they got laid off, and 1,382 said they did not. Out of the 2,900 white employees, 87 said they got laid off, 2,813 did not. Okay. So look at the type of questions we could ask with this type of table. Conditional percentages. If we want to know what's the percentage of African Americans who got laid off, well, it will be 130 divided by 1,512. That's the African American group. So that's 0.086, or we wanted to express it as a percentage, we multiply it by 100, we get 8.6%. All right. If we wanted to also express it as a rate per 1,000, we would just take the 8.6 and multiply it by 10 to get 86 per 1,000. Right. So we could say 86 African Americans out of 1,000 of them got laid off. Let's do the same thing for the white group. You see, it's much smaller percentage. 87 divided by 2,900 is 3%. You could express it as 30 white people out of 1,000. So you can see a distinct difference between those two groups. The risk of being laid off, well, the risk again is expressed as, it's the same numbers as we just did, but it's expressed as a decimal. Remember, risk is expressed as a decimal. It could also be the probability or proportion. Remember, risk, probability, proportion all mean the same thing. So we're doing the same exact calculations as before, but we leave them as decimals. Now, the relative risk would be the risk of the African Americans being laid off divided by the risk of the white employee being laid off. And if you divide those two numbers, it's 2.87. So we would say it's 2.87 times more likely that an African American is going to be laid off in this company than a white person will be laid off in this company. Another way of saying this is with the increase in risk, we would take our relative risk and subtract 1 and multiply by 100. That's how you do it. Increased risk is the relative risk. You subtract 1 and multiply by 100. When you do that, when you subtract 1 from 2.87, you get 1.87, and you multiply by 100, 187%. Now this is really, for most people, this is really where they start getting astounded by it, right? They say African Americans have an 187% higher risk of being laid off than white Americans. Wow, right? That's even a more profound way of saying it than just saying 2.87 times more. Most people would not know what that really means, but if you'd say 187% higher risk, that means a lot more to some people. So many times we want to express it as an increased risk instead of a relative risk. Odds of an African American being laid off. Let's go back to the chart. You get to go to the row of African Americans. It's 130 to 1382. That's the odds of an African American being laid off. 130 of the yes group to 1382 the no group. All right. White Americans, it's 87 to 2813. Those are the odds. Now, sometimes you may want to look at this if you want. It says the odds of an African American being laid off is 130 to 1382, and then I did a little bit. I found a number that is a common factor between 130 and 1382, which is 2. You divide both of these by 2, you could also say 65 to 691. Sometimes odds is expressed as against an African American being laid off, so that you just reverse it. All right. So the odds against an African American being laid off is 691 to 65. I'm just saying the same thing in reverse. And then for the odds of a white American being laid off, it's 87 to 2813, or the odds against a white American being laid off, again, you reverse it. Now, if you want to know the odds ratios of African Americans being laid off versus white Americans, again, you divide 130 divided by 1382 for the African Americans, 87 divided by 2813 for the white Americans. If we divide these two numbers here, we get 3.03, which says that the odds of being laid off for African Americans are 3.03 times higher than for white Americans. Okay, the odds of being laid off for African Americans. So that's called an odds ratio. Right. Any questions about that? And by the way, if you wanted to say it this way, the odds, you could subtract 1 and multiply by 100 and say the odds of being laid off is 203% higher for African Americans than for white Americans. You just subtract 1 from 3.03 and multiply that by 100, you get 203%. So you can do that with odds also. You can have an increase in odds. So that's the example. All right. Any questions? So this example is posted. All right. And again, it's in the back of this chapter. And if, again, look at some other examples in the book. But this is a chapter where you may want to read and reread it. And look at this example plus the examples that they showed in the book and on the slides. If you know how to do all these types of things, you don't have to memorize what relative risk and odds are and all those sorts of things. You just need to know how to do it. That's all. And this shows you how to do it for all these things. So in a regular course, if this is an in-person course, you'd have to memorize. Well, not memorize it. I would allow you to have formula sheets for this. Yeah. But you do have it as an open book, so you should be able to do this if you've practiced it enough. And that's true for anything in math or statistics. You need to practice before you take your test. Make sure that you know how to do these things. Any questions? We've got about 2 more minutes. If you don't have any other questions, you can just wait those 2 minutes and then you can take the quiz. No questions. Okay. So that is it. We just completed what you need to know for test number 2. All right. So once again, next Tuesday we'll have a review for test 2. Give you an idea. And oh, one other thing I wanted to let you know. We talked about using Microsoft Excel for calculating chapter 10, right? The chapter 10 stuff on regression, finding the slope of the regression line, the y-intercept, the correlation. I also created, which I will post, a spreadsheet for chapter 7 for finding the mean, the median, standard deviation of a data set, quartiles, lower quartile, upper quartile. I'll show you that on next Tuesday when we do our review. So if you want to find an easier way of finding these things, I'll give you an example and a spreadsheet, which I will post. But I won't post it until Tuesday, so that you can take a look at it with me first, and then I'll post it that day. All right, but I created that spreadsheet for you to make it easier to do that. And I also will give you links to Excel, Microsoft Excel YouTube videos, if you're not familiar with how to use Excel. All right, it's 8:50 now. So give me a thumbs up if you see the quiz. Should be available now. So yes, you see it, great. All right, so I'm gonna unshare here. I'll stop the video. And again, any questions, send something through the chat message.